Now, the fourth descriptor of kinematics or motion, all right, and it has to do with how quick something happens. So when we talk about this, we're talking about acceleration. And the word quick doesn't necessarily mean that the person is fast. It just means they're able to make, they have like quick feed, which means that they can get in and out of, if you're talking about football or sports, they can get in and out of their breaks fast and quickly. It doesn't mean that they're necessarily faster than somebody. It just means that they can do it at a faster rate. Okay, so acceleration, so it is a vector, so we got a little vector symbol there again. So it's a vector quantity that is the rate at which an object's velocity will change, and I'm going to highlight that word rate again. Again, we're talking about how it just does it over time. It is measured in meters per second squared. All right, and what that means is that for every second worth of travel, they're gaining or losing 1 meter per second. So if I'm going 10 meters per second, that means I'm gaining 10 meters per second for every, if I'm being accelerated 10 meters per second squared, that means I'm gaining or losing, I'm gaining 10 meters per second for every second. So after 2 seconds, I'm going 20 meters per second. After 3, I'm going 30, and so on. So since it is a rate, we're going to have that kind of slope look again. Right, and remember, rate signifies what is changing with respect to time. And so for acceleration, the quantity that changes is the velocity. All right. Now, when you talk about a car, there are 3 ways to accelerate. The first way is we can step on the gas pedal. Right, and by giving the car more gas, we actually speed the car up. We can, if we want to slow the car down, well, we're going to step on the brakes. Right, so these two change the magnitude of the speed or velocity. And then finally, when we want to change the direction, we're going to use the steering wheel. All right, the only way in a car to change the direction is to steer the car. All right, so the steering wheel changes that direction. And then what you should do is if you're taking a turn, you should slow the car down and then turn the car. Okay? Let's move out of the way a little bit. Now, this is just a little pet peeve of mine, and I apologize for writing this word in here. I don't generally use it. To me, it's not a nice word in physics, and that's the D word right here that you can see. I won't even say it. And the reason why we don't use that word here in physics is because it just makes the distinction that acceleration means only to speed up. So you're pigeonholing acceleration just to be speeding up. When in actuality, acceleration is the whole process, right? Acceleration is the whole thing of changing the velocity of the car, okay, or the object. If we want to talk about, well, then what do we use, Mr. Londa? Well, when we talk about speeding up, we're going to say we apply a positive acceleration, and when we talk about slowing down, you want to do a negative acceleration. So if I step on the gas pedal, I'm going to positively accelerate the object, and if I step on the brake pedal, I'm going to negatively accelerate the object. Now, when you're outside in, if you want to say the real world, you can use those 2 words to make that distinction, but inside physics, you can't, because you can't pigeonhole acceleration, only meaning to speed up. And I do lose a little respect for some book manufacturers and websites when they actually, or book publishers, when they make that distinction, because the authors are physicists. They should know that you should not use that word. All right, so here's some example problems using acceleration. So the 2015 Porsche 918 Spyder can go from 0 to 60 miles per hour, which is 26.82 meters per second in 2.4 seconds. What is its acceleration? And now this is the fast record time for a commercial car. Now, when we say commercial car, we mean kind of affordable to the normal public, because this is not the fastest time. The other two, the one car that someone mentioned was the Koenigsegg, and that's like $1 million car. Okay, so that's not something readily available to the public, where this 918 Spyder is readily available to the public. So we're going to use our definition, right, of acceleration, where it's change in velocity over change in time, and we expand out our delta. Remember, it's final minus initial. And now we just plug in our values. So we're going to do 26.82, because remember, we're using the metric system, and we're going to divide that by 2.4 seconds. Okay, and now we get an answer of, sorry, I'm typing into my calculator right now, 11.2 meters per second squared. And now, since we're accelerating it positively, right, we're speeding up, it's going to be a plus sign in front of it. So what that means is for every second of travel, this car gains 11.2 meters per second squared, right? So that 0 to 60 speed doesn't necessarily mean that the car is fast. It just means it can go from 0 to 60 quickly. And so 60 miles per hour, I can do 60 miles per hour in my Volvo, right? And I can get up to that speed just as much as that Porsche can. Okay. The next practice problem here is a dragster going 15 meters per second north increases its velocity to 25 meters per second north in 4 seconds. What is its acceleration during this time? Okay. And so what we do is, we're going to use the same formula. The difference between this problem and the previous problem is that in the previous problem, we started at 0, right? So we started at an initial velocity of 0. But if we just keep following through with our formula, V0, or V is our final, 25 is our final velocity, our initial velocity is 15, and we're going to do this in 4 seconds, right? So it's going to be 10 over 4, which is 2.5 meters per second squared. Again, positive, because we're increasing our speed from 15 to 25. Now, if you want to use the direction that they give in the wording of the problem, we would be doing this in the north direction. Okay, remember, north is positive. If you just don't forget, here's our compass. Never eat shredded wheat. And I think now people say never eat soggy waffles. But this is our positive y, this is our positive x. So north is positive, east is also positive. Okay. Now, in this last question, we're not going to do this part here, how far has it traveled during this time, because at this point in time, we don't have quite the knowledge yet to do this. We would need one of our constant acceleration kinematics equations to do that part, but we can do the top part where we talk about the final velocity after 4 seconds. So if we use our equation, right, delta V over delta T, and we expand out, right, our delta V, we got to do a little bit of algebra to get V by itself. So first step we're going to do is we're going to multiply both sides by delta T. So it cancels here, and so now I have V minus V0 plus, or excuse me, V minus V0 equals A delta T, not plus, right? Just jump it up a step, so then we're going to add our initial velocity. So that would go away. So the final velocity, we get V equals V0, right, plus A delta T. Right, and now we just plug in our numbers. Our initial velocity is 30 meters per second. Our acceleration is negative 2 meters per second squared. And there's our T, right? And you don't have to worry about the delta because this is essentially like T final, but T initial would be 0. Okay, so let's plug in our numbers. We get 30 plus negative 2 times 4. There's a plus sign. So you get 30 minus 8, which is 22 meters per second. So after 4 seconds, that this car is traveling at 22 meters per second, and you can see that our final velocity is less than our initial velocity because our acceleration was a negative number. We were slowing this car down. Okay, so that's the end of this video, and in the next video we'll talk about how does this look on a graph.